Yesterday, I have discussed the Cauchy's theorem. I like to recapitulate this once again because it is very critical and difficult subject. Let me explain up to my end again and again because I have to use this everywhere. Now, what is this stress? This theorem, Cauchy's theorem, tells us the stress components on an ideal plane. What means this. What does it means is, say we have a certain body, some prismatic bar, and it is subjected to certain type of external load, and it also has its body forces, like at least gravitational forces must be there. It may have some magnetic force, it may have some inertia force, everything. So that as per our previous discussion, this particular prismatic bar is subjected to external forces, maybe point load, maybe external distributed load, and subjected to the reaction from supporting supporting supports, and as well as the surface forces, or I'm sorry, body forces, like at least gravitational force must be there, and it may have magnetic and everything, and inertia force like this. And now, if we select a particular point on inside its body, or maybe on the surface of the body itself, then what we'll see, that if we know the certain components of stresses on that particular part, the particular points, say sigma x, sigma y, sigma z, tau x, y, like this, I will explain it later. Then we'll go through the, we can calculate the force acting over on any plane passing through that particular body, particular point. So what we need, we have to know the point inside the body or on the surface of the body, whatever it may be, and this we should place the three mutually perpendicular axis on this point, and so that, and we should know the stresses which is acting on this point, say along x-axis and y-axis, maybe tensile and maybe shear stresses in nature. We know at these stresses, and we should know the vector reaction cosine of any of a normal n acting at the acting emerging from the point, our set point P, which means the reaction cosines of this normal means the angle which the cosine of the angle which this normal makes with x, y, and z axis. We should know these things. Angle, this reaction cosines may be same if the angle is same, and it may be different if the angle is different itself. So with so many inputs we have, then what shall you do? Say three mutually perpendicular planes. What is going on in the space is, this is, I have forgot to write this is A point, B point, A, B, and C. 3 points is not being seen here, but it is there. A, B, and C. Now, what we have here, three mutually perpendicular planes, that is XY plane, ZYZ plane, and ZX plane, is passing through this point P, which is the set point whose all type of stresses we are supposed to calculate by this Cauchy's formula. And there is an arbitrary plane identified, and any arbitrary plane will be identified by the normals n whose reaction cosines are given. So there is a normal which is normal over the plane itself, and whose reaction cosines means cos of the angle this normal makes with x-axis, with y-axis, and with z-axis. This is known. The stresses sigma x, sigma y, sigma z, this is known, and the shear stresses tau z of different shear stresses of different of the same points on the same planes also known to us. So what we do, what we have, let us consider now, just already we have a this, like any arbitrary plane is identified by outward normals n. Okay. So we need, what is this arbitrary plane? What we let us do, let us consider a small tetrahedron, means a triangular pyramid passing through the point itself. So, in the point P, the rectangular triangular pyramid means all its faces are triangular. There are four faces: one, two, three, and this ABC face. There are four faces. There are four apexes. There are four apexes: one, two, three, and four of the plane itself, and four sides: one, two, three, and four itself. So we have four planes, four sides, four apexes. We have four plane, four side, and four apexes here. Now, let us first consider the plane ABC, A, B, and C. This triangular plane, which is not passing through, only other planes are passing through P, but this triangular plane A, B, C is not passing through the P, but is away from P. And let us that H is the distance of this plane P from the point P itself. Now, let us isolate this tetrahedron from the original body of our prismatic bar. So if we isolate and make a free body diagram of certain portion of a loaded prismatic bar, we have to show the original given forces over it, as well as we have to show the reaction of its adjacent face over it, and this reaction should be a force of certain orientation and magnitude, but we should have the same force acting over its adjacent side, which means this is like nullifying each other when it is assembled. Because this force doesn't exist, we have just imagined to make the free body diagram here. Here we have the force like this is a force sigma x. Now Tn is a force Tn. Just 1 second, please. Now, now, then it will be equal. Now, if we tetragonal is isolated from the body and a free body diagram is drawn, it will be in equilibrium under the action of the surface forces and body forces. The free body diagram is shown here, which is just shown here. That is the free body diagram. Now, we are considering the size of this tetrahedron is extremely small, and in the limit, we are we are making the h, the distance of the point P to the face of the side ABC is tends to 0. It's almost 0, but not equal to 0. Those are the mathematical terms we use. And in terms of overall stresses, we shall speak in terms of the overall stress present over the faces itself. Now, this Tn, the resultant stress vector on the face ABC, which is we show the imaginary forces which is acting over the face, and which will be which is being balanced by a force of equal amount but opposite direction on the same adjacent side of the body itself, and which, if we assemble, will nullify each other. Now, but here it exists because we are using the free body diagram, and we are resolving these forces in along x and yz axis and writing down the force Tx, Ty, and Tj. It is a vector, and it is parallel to the normal n. That's why n is written on top of it. Now, on the all three faces, stress components are there. On the x plane, sigma x is the direct stress, tau xy and tau xz. It, you know, the x is the by the subscripts x, we means the it is acting over the x plane, explained, and it is directed along y plane. Same is the case here. It is along acting along z plane but directed along the y direction itself. So we have on the xy planes sigma x, in the x direction we have sigma x, tau xy, and tau tau xz. Just 1 second, please. Uh, hmm. Same is case of sigma y, tau z, yz, tau yx means sigma y is a shear stress in y plane, and tau z and tau yz and tau yx is the shear stress acting acting on the y plane but directed along the z axis, and shear stress acting along y plane but directed along z axis itself. Same sigma x, sigma z, tau z is a similar explanation. Now, if A is the area of the inclined face, then what we see, the area of area of BPC, or projection of the area AB made on the YZ plane. We are getting, as we know, the area ABC is equal to A. We are getting this projection by multiplying the cosine uh, cosine vector by reaction cosine by A. So the area projected area BPC is equal to A into NX. That is, CB is a projected media in the XZ plane, ABC on XZ plane. So A into NY is the direction cosine along the Y direction, and APB projection on the area IBC on the XY plane, where A multiplied by NZ. NZ is again direction cosine of the normal N along Y direction itself. So now we know we have to know the body force. We have to take the body force under consideration. We put the body force in the x, y, z direction and given as sigma, gamma x, gamma y, and gamma z, respectively, as per volume. Now, the volume of the tetraangle we are supposed to know, because all these body forces is given as per the unit volume. The volume of this tetraangle will be 1/3 the area of the base in multiplied by the height. Sorry, where h is the perpendicular distance from P. H is the perpendicular distance from P to the inclined face itself. For example, equilibrium of the tetrahedron, the sum of the forces in x, y, and z direction must individually vanish. So, equilibrium in the of the tetrahedron means it's perfectly balanced and no unbalanced force is there. And so, any forces, sum of the forces x, y, and z direction should be equal to 0, or they are balancing each other to make the tetrahedron in perfect equilibrium. So, what will happen? Txn, which is the component of the force T along x-axis multiplied by the area A, minus sigma n, it is opposing it. Sigma x is the normal force in along x direction, and A nx minus tau yz is the normal force. It is the normal force along y direction on x plane multiplied by A n y, the portion area along area of this area of the triangle, component of the area of the triangle is A multiplied by the direction cosine along y direction minus z tau zx. It is the force acting along z axis but on x plane, acting towards the z axis but acting on x plane itself. So A n z is the area of the plane ABC multiplied by the reaction cosine nz, which is the cos of the angle the normal of ABC makes with y-axis itself, plus 1/3 A hx, where A one third AH is the volume of the body force multiplied the volume of body force along y axis, component of body force along x direction. So we are equating to 0, and we have to cancel A because everywhere the A is there, and uh, thus this becomes Tx n equal to sigma x nx, Txy ny, sigma x zx minus one third h gamma x. Similarly, Ty and Tz is calculated, and in the limit, as h tends to 0, the oblique plates will almost pass through the point P, and the average stress acting on the faces will tend the respective values to the point P. So all these stress components acting on the faces, all these x, y, y, z axis will tend to their values on respective values at point P acting on, just 1 second, share 7, 8. So this equation we are written jointly, and the equation becomes that one third AH into sigma y vanishes as h tends to 0 itself. So all these forces Tx, Ty, Tz is given by the relation Nx, Ny, where all uh, this force Tx, Ty, Tz is tending towards the central point P, and all other existing forces are also tending towards X itself, and it was P itself. And this equation is defined as Cauchy's stress formula. Now, what it shows, the equation shows there are 9 variables like sigma x, sigma yx, sigma zx, tau xy, sigma y, tau zy, and tau yz, tau ny, tau yz, tau tau yz, it is tau zx. This will be tau zx and tau yz and n2. This is wrong. This is z. It should be zx, not yz. Now, uh, this gives us that this will all these 6 stresses, 9 stresses. Among these 9 stresses, we know there are 6 independent stresses, as if sigma x, sigma y, sigma z. This is the other 3, and other 3 are tau xy, yx is equal to tau yx, tau yz is equal to tau zy, and tau zx is equal to tau xz. These 3 stresses are equal, and so there are altogether there are 6 unknown stresses, and this equality of the shear stresses are defined as equality of cross shear, as equality shear stress in one direction will be shear stress acting on x direction, shear stress acting on x plane and pointing towards y direction is equal to shear stress acting on y plane part pointing toward x direction. These 2 shear stresses are equal as per the shear equality of cross shear. Now, so this Cauchy's theory is divided into, reduced to Ti, means the direction to which the stress is acting. I mean, the axis to which the x is acting means it can be x, y, and z, and nx and ix. Everywhere I is used to denote the axis to which this stress is acting. In case of sigma, this is sigma ix. If it acts towards the x-axis, it will become tau xx or sigma x. And other side, it is tau xy and tau xz like this. Or again, we can reduce the summation of j, where x, y, and this x, y, and z are all given as nz itself. And next process is also j, because x, y, and z can be put in sequence here to get the Cauchy's theorem. Now, now if the Now sigma n and sigma are normal. Actually, the normal resultant stress on the plane ABC is given by t square is equal to tx square, ty, and tz square. Well, all are along the normal x. Is as they are all vector, it should have a line of action, and they are all acting either normal along the normal or parallel to the normal x. It's normal n. Now, there this normal n may not be exactly this force Tn may not be exactly normal over the face AB. It may have some component sigma n, and it may have some component sigma n and tau n, which are normal stress and shear stress over acting over the plane ABC from resulting from Tn itself. So Tn is equal to sigma n square plus sigma tau n square. So there are two ways we are referring for T. T is equal to, one is here in terms of Tx, Ty, Tz, and another in terms of sigma n and tau n. But we are supposed to calculate the value of sigma n using these two equations. How we can do it is like this. The normal stress is equal to the projection, just I have told you, and equal to the sum of the projection and the projection of the components Ti, Tx, Az. Sum of the projection of the components, which is sum of the projection of the components Tx, Ty, and Tz. So sigma x is the projection multiplied by Tx. Tx is the projection multiplied by cosine, means it is the projection along x-axis. This is the projection on y-axis, and this is the projection of along z-axis. So sigma n is the sum of the projection of all the respective stresses itself. And this substituting, if you can put the value of Tx, Ty, and Tz in this equation from the above equation, and this equation will take the form of like this. Sigma x is equal to nx squared sigma x, ny squared sigma z, and z squared sigma z, sigma y. This should be sigma y itself. And plus 2 ny tau xy, 2 ny nz tau xy plus 2 nz nx tau xy. If we simplify, this will take this particular form for sigma x, where we are supposed to know sigma x, z, and x, y, and z, and tau xy, tau zy, and tau x, and all the relative direction cosines. So you can get sigma x, and from using this equation and knowing the value of sigma n and sigma z, we can get the value of tau n. So this is the method of using the Cauchy's formula to calculate the stress, normal and shear stress at a point. When the normal is known, the direction cosines of the normal is known, means we know the orientation of sigma x, because normal defines a particular stress, and by defining means it is giving you the direction cosines as from which that is the cos of this angle subtended by this normal to x, y, and z axis. And if we know the value of sigma x, sigma y, and tau xy, etc., you can safely calculate this normal force sigma n and tau n acting over the plane itself at that particular point P. As the normal plane ABC is tending towards the point P, and the distance is infinitesimally small, so acting by calculating sigma n and tau n square, we can safely know the normal stress and sigma stress over that particular point itself. Let us go through few practical sums. I have already told one of them. What we have here in this sum is a rectangular steel bar having a cross section 2 cm by 3 cm and is subjected to tensile stress of 6,000 Newton or 6 kilonewton and equal to 612.2 kgf, And if the axes are shown in the figure, if axes are drawn as per shown in the figure, like say x, y, and z, then find out the normal and shear stress on a plane whose normal has the following direction cosines. So what is given here? First of all, what is the size of the block? 2 centimeter, 3 centimeter. What is the load acting over the block? It is 6,000 Newton or 6 kilonewton. And acting which direction? It is acting over direction over the y-axis. So there is no external force acting along x, acting along z-axis itself. From the very beginning, we don't have sigma y and sigma z. Now, next is the direction cosine of the plane. Next, we have to find out, this is the loaded. Now, we have to find out the normal shear stresses on different planes. And we should know at least the orientation of the plane with the x, y, and z axis, which means we should know the direction cosines of this particular plane itself. So we are given three different planes. One for one, nx and ny is square root of 2. Nx and ny nx and just 1 second. Nx and ny is the nx is equal to ny and 1 by root 2 and nz is equal to 0. Means and along the z axis you don't have any component at all. So this is the plane has components along x inclined to x and y axis, and it is not inclined to z axis itself. So what we have here, area is given, so we get the cross sectional area 6 centimeters square. What will be the average stress? 6,000 by 6,000 Newton per meter square. And what is this is the normal stress, sigma y, sigma z, and sigma x is 0. Here we get only normal stress is there, sigma y, along y direction. Sigma x and sigma z is already 0, as per that there is no force is there. Now, let us use this equation. Let us use this equation, Tx, Ty, and Tz equal to so and so things. Now, what will be T squared, Tx, Ty, Tz, Tx squared, Ty squared, Tz squared. And we know another equation is there, T squared is equal to sigma n plus sigma n square. That's why sigma n here is given as sigma x Tx, sigma y Ty, sigma z Tn. Now, reaction cosines. The reaction cosines is given as nx and ny square root and nz is equal to 0. Sigma x, sigma z is equal to 0, sigma y is equal to 1000 Newton per meter square. And towards the direction of z, towards the x-axis, y-axis, z-axis, x-axis, z-axis, y-axis, all the taus are 0, as there is no force acting on y and z-axis itself. And tx to the power txn is equal to ty. So we here tx will be 0 because you have to put all these 0 values to this equation. Sigma here sigma x, sigma nx and sigma is 0, and ny is have value, but tau x y yz is 0, 10 z and z both are 0. So tx is equal to 0, ty remains. Only this portion ny and sigma x remains. Others are equal to 0 itself. So ny is equal to square root ny is equal to ny into sigma y is 1 by square root of 2 into 1000, or tau c tc to the power n is also equal to 0 itself, tz. And tz, not tc, tz will be also equal to 0 itself. So sigma n from this equation, which reduces to here, will have square root of 2, that is ny, 1 by root 2 multiplied by 1 by root 2 into 1000, which is equal to Ty, which is given here. So sigma n is equal to 5000 Newton per meter square, and T square will be equal to as uh, T square. T square is also equal to this one. So T square is equal to square root square of Ty. It is 1 by 2 into 1000, which is given here. Thus, this becomes 1 lakh. 1 lakh by 2 is equal to 10 lakh by 2 is equal to 5 lakh itself. Uh, now put the value of sigma n is equal to 5 lakhs. Sigma t is equal to sigma tn is equal to 5 lakhs, and sigma n is equal to 2 lakh 50,000, 2 lakh 50,000. So sigma tau n is equal to 25 2 lakh 50,000 itself, or tau n is equal to 500 Newton per centimeter square. Now, so we have solved one of the problem itself. Now, uh, the problem 2, uh, Tx here what is given, Tx is equal to 0. What is given here, for the same loading of the plane, here is also Tx is equal to 0, Ty 1000 by root 2, and Tz is equal to 0, because along x-axis, along z-axis, there is no force. Only we have the force along the y-axis itself. And sigma n is 500 centimeter square. We have already calculated that. Now, we know here tau z, and we know here tau z and Tz and Tx is equal to 0 itself. This Tx and Tz, this is a 0 because there is no force there. So Tn square is equal to Ty square 1000 by root over 2. And from T, sigma square, sigma tau n square, where sigma square already calculated 500 millimeter itself. So tau n is equal to also 500 millimeter, because sigma n, we know that this one and we know this one, and if you divide from here, this from here, you will get 500 Newton per square meter, which is the same as the earlier problem. In the third problem, what we have, Tn Tn is equal to 0, Ty is equal to 1000 by square root of 3. Earlier it was square root of 2, and Tz 0, because again I'm saying the same thing. It is along x-axis or along z-axis, there is no force, only y force is there on y-axis. So any plane acting of this particular prismatic bar, there is no force along x and y-axis itself. So here the total force acting, Tx square, Ty square, Tz square is 1000 by square root by 3. Now, equation Ty to the power n, it's ny sigma y is equal to square root by 3. Then ny is given as from equation to Ty will be ny sigma y as 1 by square root of 3 into 1000 itself, or 1000 by square root by 3. Thus, ny into Ty, ny is square root by 3 into Ty, 1000 by square root by 3, the 1000 by 3 itself. Now, what happens? What happens here? Sigma n is n. We put the value ny is given as 1 by square root of 3, and we calculate as Ty 1000 by square root by 3 is equal to 1000 by 3 Newton per centimeter square. So from equation 5, we'll get we put the value of sigma, we put the value of Tn as well as sigma, which is 10,000 to the power 4 by 3, 10,000, 1,000 to square divided by 9, which is equal to 471.4 Newton per centimeter square. It is the force given on the axis itself. Another thing, let us go through another problem. Now, at a point P in a body, at a point sigma x is given as 10,000 Newton per centimeter square, sigma y is given as minus 5,000 Newton per centimeter square, and sigma z is given as 5,000 Newton per centimeter square. And all tau xy, tau z are equal and 10,000 Newton per centimeter square. So determine the normal and shearing stresses on a plane that is equally inclined to all three axes, which means there a plane that is equally inclined to all three axes are would be nx equal to ny and nz is equal to 1 by root 3, as na square plus ny square is equal to 1 itself. So this is put, and you will get nx, ny and nz. So we have sigma x, sigma y, sigma z, all nx, ny and nz, and all tau xy. We have to find out the normal shear stress on a plane, on the plane itself. Let us have this triangle OAP. O is here, A is here, and P is here. This is a block whose apexes are A, P, and C, and O, and D, B. What is along y-axis OB, along x-axis OA, and along z-axis OC. Now what we have, the triangle OAP is a right angle triangle at A itself. Then cos alpha is given as x OA divided by OP, or x divided by R itself. X is the length along x-axis, and R is the diagonal length OP. Similarly, the right angle triangle OTP and OCP. Right angle triangle means OC, OBP, and OCP. Like this, what we have, the cos beta and cos alpha is y by r, y divided by r, and z divided by r itself. And respectively, and similarly, r is also square root of x square plus y square plus r y square plus z square. So thus cos alpha becomes x by r, beta y by r, cos gamma z by r, for which this alpha beta thing, from which that can be obtained